Now we're going to be integrating this from 1 to number b, and that way we'll be able to take care of it. Actually, people like to put x dx, but looks like whether it's x or n really makes no difference when you integrate. So power is -4 divided by -4, right? According to, actually -2, I need to add one, not subtract. I need to concentrate. So x to the power of -2 over -2. We increase the power by 1 and put the same number in denominator and then go from 1 to b. And of course, don't forget about our limit. So when you do this, then it looks like I have a -1 over b squared. And then subtract -1 over 2b squared. 1 over 2 times 1. And of course, b is sent to infinity. And therefore, this piece is going to be 1 over big or small. So I get a half, and that's finite. The key part is finite. We don't know what the actual integral is, but it's convergent because it's finite. Sorry, we don't know what the actual sum of the series is, since the integral is 1/2, which is finite, then so is the series is finite, and we say word converge. But you don't really have to do it in such a heavy way. I only expected you to look at the oh, it's number 1. Okay, we'll also look at number 1. So we have to take a look at the series that is appearing here in their definition, or so-called P series. So the definition is actually telling us that when you have the P series, or in our case, let me look at this again. I think that's a good exercise. So 1 over n cubed. So this is our power. So they call it as letter P. So if P is greater than 1, then the series is going to converge. And that's really all you wanted to say here. So you don't have to check this out. But we checked this out, and the power is 3. It is definitely greater than 1. So the series converge. Now, if power is less than or equal to 1, then the series is not going to converge. It's going to diverge. And this is what we observe with a series 1 over n. Of course, they all go from 1 to infinity. So n starts at 1, then 2, then 3, etc. And in the exercise number 1, we are going to actually experience the series, which is a friend of 1 over n. Please notice that I could somehow say that this is going to be analogous to 1 over n. So this is going to also diverge, right? So in exercise number 1, we have divergent series because it's analogous to 1 over n, but you can take the antiderivative, that be ln, and then put n to infinity, and the limit will be infinity. But the point of this is not to every time start doing it. You see the series 1 over n analogous to that 1 over n plus 3 or any number involved with letter n, just like in exercise 2. It is also going to diverge because it's also equivalent to series 1 over n, but it happens to be multiplied by 2/3. But that 2/3 makes not much difference when you're dealing with infinity, so it's also going to diverge. And the idea I'm trying to come across right now is comparison series that very nicely shown in the special test here, the comparison series test. So if I have two series, 1 over n plus 3 and 1 over n, why do I say they're equivalent? Well, because when I'm going to consider the limit of their n's terms, so when limit is taken of an divided by bn, so when I divide their n's terms, so if I take 1 over n on the top and 1 over n plus 3 on the bottom, then I can flip that second fraction. I can flip that second fraction, so we still have a limit, of course. So we're going to deal with a limit of n plus 3 is in numerator, and n is in denominator, right? And then say by L'Hopital's rule, when you take derivative of the top and the bottom, since our n always approaches to infinity, right? It's infinity over infinity. When you take derivatives by L'Hopital's rule, you get 1 over 1, which is a number which is finite. That's the key idea. So the number has to be finite. They say, and they also want it to be positive. Well, they say the nth terms are greater than 0. So if you divide two positive numbers, it is going to be positive. So I'm not sure why they trying to stress the fact that it is positive, because we divide two positive numbers anyways. So if number is finite, and it is finite because it is 1, then these series behave the same way, which means that if I know that so-called harmonic series is divergent, we saw this last time, then this one is also going to be divergent. So notice that we have another way to determine behavior of series in terms of being convergent or not. So we comparing it with the series that we know. And this comparison idea is real big, and it is always very useful for the exercises, because lots of times you see the series that have not a very pleasant look, and you can just disregard everything but the power of denominator, and then right away you can say that this is going to be already either convergent or divergent series. So let me take a look at the next section and do some examples. My message here is that there are various ways to do the same exact exercise. So you can do it using, say, geometric series approach, or you can do the comparison of the series like we do right now. So what we again care about is a limit of the n's terms, And once you divide those n terms, when n is, of course, approaching to infinity, so infinite series, then if you have a finite number, say L, then both behave the same way. That's the key idea. Like, for example, exercise 3, we have the series analogous to 1 over n squared, right? And 1 over n squared is convergent, isn't it? Why? 1 over n squared is convergent. Well, we call it as a p series, just like we started working with 1 over n cubed today. So it's p series, power is greater than 1. So it is convergent. So it's 1 over n squared convergent. Then by the special statement above, the series 1 over n squared and whatever else is involved with it, as long as power of n is going to be the 2 on the bottom, is also going to be convergent. That's pretty neat. And of course, one is Alex, but you really need to take that limit here. Yeah, you can take the limit, so you can just spend some time writing. You will do it once, you will do it twice, and then eventually you will say, okay, that's all pretty much the same. But why not? Let us divide 1 over n squared on the top and 1 over n squared plus 1 on the bottom. And of course, one can say, who told you that 1 over n squared could be on the top? Maybe it's on the bottom. It doesn't matter, again, because what we care is a limit of this quotient, and the limit will come out as a finite number. So if I flipped this denominator, so n squared plus 1 will be now in my numerator here, and that 1 over n squared, so n squared will still be on the bottom. Then either using L'Hopital's rule, or since the degrees of these polynomials are the same, so I can just get quotient of their leading coefficients, which is 1. Then I say, as harmonic series above, it's not harmonic, but p series is convergent, then, this little sign, then the series we have is also convergent. Again, as this limit is finite. So just to justify it like that will be great. So such a limit is finite, then that's it. So it looks like the key idea is to find the series that we can compare ours with, and looks like the group of series here is pretty clear, like exercise 5 is dealing with the divergent series analog, right, with 1 over n, that's the one we just noticed, and here that it is divergent series, so will be the series 2n minus 1 in denominator. So you can always find that limit and see it's finite, like 1/2 or something. So divergent. How about 6? Is it also equivalent to divergent series, which is 1 over n to the power of 1/2, right? So square root of n. So remember the theorem that we already utilized today. If p is greater than 1, the series is convergent. But in the example that I just found, this power is less than 1. So say it's divergent because 1/2 is going to be less than 1. And again, why? Well, let us just scroll up to the test that we had in the previous section. So it turns out that previous section is one of the key sections, because we're gonna see these P series throughout the class a lot. So whenever you have a series with the power P, which is less than 1, it is divergent. Like if you have any series that will look like with a square root, like 1 over square root of n, or a cube root. So all those radicals, so powers of n smaller than 1, right? Because that's same as a one we have here, n to the 1/2. Or that one is 1 over n to the 1/3. So if powers of n and denominator are less than 1, the series are divergent. So there are two sides in this test, and that's, I think, a great test that we going to use a lot. And that's why I think it's good to know where it is located, so you can always refer to it or write it down along with this theorem that I just have here with that series comparison test. So let's go back to these exercises and take a look at some more of these. So like in problem number 23, for example, this is going to be analogous to what series? 1 over n squared, right? Again, why do I use the word analogous? Well, actually, utilizing this test, the limit of n's terms. So you can always try to find such a limit, and you will see that this is a finite number. Looks like it's going to be equal to number 1. So we get convergent series. What about the one here, number 27? That looks a little different. It deals with a sine function. So let me take a look at that one. I'm gonna get some room for this. Like I say, that's 1 over n. Well, it's a sine function, right? So what is going on then? Well, let us get a little room and see what kind of function we're actually dealing with here. So notice that to graph this function, I can use 1 over x, turns out on the other side as well, as the asymptote. And then the sine will be going in between. It's like 0, and then there's pi, and there's a 2 pi. But if it's a 1 over n, when n approaches to infinity, so it looks like the values start at 1, but then it's going to be smaller and smaller, so the y coordinates are smaller. So you select the points and you add them together. So what kind of function are we actually working with? In other words, can I say that series sine of 1 over n will be actually equivalent to the series 1 over n? Well, you have the way to check. Just take a limit. So you don't have to guess, but get yourself a limit and see how this is going to come out. Is it going to be a finite or not? Remember the key idea. If it's a finite, then they both behave the same way. So let us try. So what I'm going to do is have again limit of a quotient of 2 And for the upper one, it'd be a sine of 1 over n. And for the lower one is just 1 over n. Right? Remember, there was a special limit, sine x over x, right? But that happened when x was approaching to 0, right? So in our case, n approaches to infinity, but notice that if n approaches to infinity, then 1 over n approaches to 0, isn't it? So I can actually utilize this. I can replace and say, if I call my 1 over n as some letter k, so when n goes to infinity, k will go to 0. And I turn this into the limit of sine k over k. I say, Alex, you told us that letters make no difference. They don't, but you can call it as k or x. But the point is that now I have that special limit that was equal to, remember what? There was some number. Sine k over k. If you're not sure, take derivative. It is 1. It's a special limit that we talk a lot about in the calculus 1 class. See, the time passes by and people forget things. So the limit of sine x over x when x goes to 0 is 1. So how do you know that? Well, you can do it quickly. Just take the graphing calculator. Remember, we have the graphing calculator for free here. The graphing calculator, the decimals that I like to use for illustration. So I take sine x. So I need to go to the choices for my functions. So where do I get functions? You see here. So functions. And here's a bunch of them. So I put sine of x. And then I divide this. Let me make sure I get out of parentheses and divide this by x. So what happens when x approaches to 0? Do you see what function approaches to? Y coordinates. So when x approaches to 0, this function approaches to 1. And indeed, that's what we know about this limit. So it is 1. It is finite. That's the key part that what we are trying to find out. So if it is finite, they both are going to be divergent series. So it's interesting. That's exercise number 27. So other than that, I think all problems here are pretty much same. I say maybe 31 is a little different. Yeah, that's a geometric series, right? It's 1 over 5 to the power of n. Analog, right? And that's a conversion series, isn't it? Because remember, the ratio is 1/5. That's another little statement about special kind of series, geometric. So we keep multiplying by 1/5, 1/5 times 1/5. So make it 5 times smaller, 5 times smaller. The terms gets very, very small. So if it's a same ratio, we call it geometric series, and it is convergent when ratio is less than 1. So looks like there we have it. Another convergent series. So how about other stuff this section is talking about? It's not it. It turns out there is another way to work with series that actually is less, I don't want to say word workable, but kind of less appealing, because sometimes it takes lots of play with inequalities. I want to just take a look at example 2 today. We'll be using this method. In fact, in later math classes, that's the only method that you can use, turns out, because usually we use it when series don't go under any other approach. So for example, here, you don't really need this method because you already see it's equivalent to 1 over square root of n, which is divergent, right? So you don't have to worry much about it. But what it says here is that if you look at the terms of 2 series, of this series and that, and if you notice that 2 plus square root of n is going to be always greater than square root of n, isn't it? Why is that? Well, because I add 2 to one side. I have same thing, but then on the left side, I add 2, so it bumped it up by 2. So it's definitely going to be greater. Well, they like to put greater than or equal to be on the safe side, they say. So then what they do is they flip the left side and flip the right side. And notice that when you put bigger number in denominator, it becomes smaller. So the inequality reverses its direction. And then what I can conclude, so I have the series here, which is going to be divergent, and the terms, yeah, it doesn't meet requirements. I think this exercise, I'm not sure why they put it here. Unbelievable. I'm sorry. I didn't read this example before I started, and then I noticed that I cannot use this test. Well, we just did the exercise like that, right? We already know that they both be divergent, but turns out I think it's good that I actually get into this pitfall, because the thing is, if you have series with terms that are greater than mine. So for example, if they put the series not like that, but say series will be square root n minus 2. So that series, if you compare square root n with a square root n minus 2, then minus 2 will give you less, right? Because you subtract 2, you can make it small. But if you flip both of them, then the inequality is also flipped, because when you divide by smaller, you get bigger, right? When you share with less people, you get yourself more compared to when you share with more people, then you get less. Well, that's why I don't want to share. Well, that's not the point. The point is, the more pieces you break your amount, the smaller it becomes. So we got the smaller in denominator, so the result is going to be greater. And then what happens? I can say that the sum of series here is going to be less than the series below, right? Because below we're adding greater pieces, so the sum is definitely going to be more than when I add the smaller pieces. But notice that that one is divergent. We know that, right? We just stress this number of times because this is E-series. And that's why, since this is divergent, the sum is actually infinite. But that one is even bigger. You see? It's even bigger. When you say Alex enough, I see it's bigger. So If that one is infinite, so be that one. And that's the argument that they tried to get across, but they didn't select a good example for that. Well, actually, I would say they didn't select a good series to compare it with. They could have selected something with a little bit of sophistication and algebra. But again, you start to get into all this algebraic inequality play, and that's why it is not really that, I guess, straightforward. So I think the example one much better illustrates the story. So notice that here they are comparing with a geometric series, right? So 1 over 3 over n, we know it's convergent series. And what they do is they say that if I look at 3 to the power of n and 3 to the power of n plus 2, then 3 to the power of n is definitely going to be smaller, right? So if I take 1 over 3 to the power of n and 1 over that bigger thing, then that bigger thing will be now less because inequality flipped. And from the fact that we are having this geometric series which is convergent, so this is going to be something finite. Convergent means the sum is finite, right? And positive, of course, because the terms are all positive. Then the smaller one is also going to be finite. It can't be infinite because it's smaller. You see, that's the other side of idea, this argument. So then this one is also convergent. So that's direct comparison of series test, and that's what they actually talking about. I think this deserves time to be, I guess, spent on thinking, because it's not obvious. This is not obvious. That's what we learn in later math classes and some advanced calculus kind of stuff. And that's why I want to just introduce you with that today. So next time we'll look at it again a little deeper, so you will hopefully feel more comfortable, because this idea of comparison inequalities, I guess, is the least pleasant part of series, because sometimes it's hard to find the right inequality for your comparisons. That's why I would say some exercises sometimes take a little bit of a time. But anyways, once you saw this idea, and then you will see it again, and then I'm sure you will eventually encounter more exercises that we'll be able to do by comparison, then I hope you will feel pretty good about this. So anyways, let me try another problem here, and then have you try one as a little quiz for a similar series. So how about if I try one, but I need to clean all this messy. I will try exercise number 8, and you can try exercise number 7. So all you have to do is determine if series is convergent or divergent. So if I look at the exercise number 8, then right away I ignore that 3 on the bottom. So I have series that looks like 4/5 raised to the power of n. And this is convergent series. Why? Because it's geometric. Because the ratio is 4/5 less than 1, geometric. Okay. Therefore, by the quotient of n's terms being finite, 4/5 and 4/5, it'll be just 1. We have the original series convergent. So all you have to do is just say word convergent, and that'd be the answer to our today's little quiz. So how about problem number 7 for quiz? Just tell whether it is convergent or not. So for exercise number 7.